So instead of E, no, let me write V only. What is RMS value of this signal will be VRMS. Then at any instant of time, let Q minus Q. So what is Q should be equal to? Q should be equal to C into V. What is V? V naught sine omega. I'll differentiate this. dq by dt. C V naught cos omega t. So this dq by dt is omega sine omega t. dq by dt is what? I'm going to write it I is equal
cos
to
omega t.
Sine differentiation of this will be cos omega t. This will write it in the Ohm's law form. I'll bring quantity called as xc cos omega t. What is xc? Xc shall I write 1 by omega c? This is called as capacitive reactance. All of you very important, because the rest all everything I'll apply the Ohm's law, KVL, KCL, but these are very important. I'll call capacitive reactance, a word you say, reactance, not resistance, reactance. And it depends on the capacitance and angular frequency. So finally this equation will end up I equal to I naught cos omega t. So look at the current and voltage characteristics. If I plot this, this applied voltage. What about the current? The current is cos, no? So cosine. Oh, some. Try to see this variation. The black color is what? The applied voltage, and the red color is what? The current. Anything is happening to them. Shall I say current leads the voltage? So if I write in phasor diagram, every time drawing sine waves will be a very big problem. 0 degrees, pi by 2, pi, 3 pi by 2. Instead of 3 pi by 2, I'll write it minus pi by 2. Now I'm bringing phasor diagram. So if you go back to the vectors, so look at this current now. What is the phase of the voltage? Sine omega t, 0 phase. The voltage lies along x-axis. What about the current? The current is what happened? Cos omega t. It leads the voltage by 90 degrees. So the current is so across capacitor, the current leads the voltage by 90 degrees. So now so suddenly, sir, why you brought this 0 to pi by 2? You go back to vectors, you take a force. Suppose a force F1 equal to 10 Newton, 0 phase, acting along 0 degrees. Another force, 5 Newton, acting, so what is the J cap? J cap is along y-axis. No, I cap means along x-axis. Instead of saying x and y, the quantities which are having 0 phase will be along x-axis. The quantities which are having a phase of 90 degree, I'll take y-axis. The quantities which are having phase of 180 degrees, it will be along negative x-axis. The quantities which are having minus 90 degree will be along negative y-axis. Or you can write 3 pi by 2. It's left to you. Sir, what about quantities which are having phase angle 45 degrees? That will come in between. So now what is the length of this vector? Length of this arrow will indicate the magnitude. And what about the phase or the direction? The direction is mentioned by this system here, 0, pi by 2, pi. So definitely I say that the current leads voltage by how much? 90 degrees. Because cos, what you write it as? Sine omega t plus pi by 2. Am I right? So what do you mean by plus pi by 2? It is having a phase of pi by 2. So I represent. This is called like a phasor now. So what about current voltages in AC circuit? They are vectors. Simplest way. Conclusion. You cannot take the algebraic sum. You have to take the vector sum of voltages or currents. Even the powers also here. There's a phasor diagram. Any quantity having a phase of 90 degrees, it will align. It will get aligned along y-axis. If it's having a zero phase, it will be along x-axis. If it's having minus 90 degree, it will be along negative y-axis here. If it's having a phase of 180 degree, we'll put along this direction. Slowly, I'll introduce to complex numbers tomorrow. What you studied complex numbers, I'm going to use it here. Why we study complex number? To deal with electrical circuits, not just to solve the mathematical problem. Now you can see the total application of the complex numbers, what you're going to study. Okay, this is about the, so shall I say current leads the voltage. Tomorrow, if rest are connected, tomorrow we'll see. This is about the thing. So shall I put here, current leads the voltage. So we just show across capacitor, you have to show like this. This is the voltage, zero phase we have took it. What about the current? Current will be like this here. No, I'm interested in the power. We'll see that what happened to power across the capacitor. So we have equation for current and also the applied voltage. What is applied voltage? V naught sine omega t. Instantaneous power equal to V into I. V naught sine omega t. I naught cos omega t. So V naught I naught. This will be by 2 sine 2 omega t. What is the average value of sine 2 omega t in one full cycle? Should be 0. Is it okay? Sine 2 omega t, average value of, or say like a sine 2 omega t in one full cycle will be 0. So therefore, what is this capacitor? It will not dissipate power. Means it's just a storing element. We know it's a storing element. It will not dissipate power. So this is something very important. So what is the role of capacitor? It will not consume any power. But what it's doing, it is making current to lead voltage. That's why this reactance. So what is the capacitor? What it do? It will make current to lead voltage. Will it consume any power? No. So then how to write Ohm's law across capacitor? The Ohm's law across capacitor will be V is equal to I into XC. V naught equal to I naught into XC, or VRMS. I'll come to later on, because we have to write VC into IRMS into XC, like this we should write. So tomorrow in detail I'll go. For time being, what is the Ohm's law across capacitor? It should be drop across capacitor into current into capacitive reactance, not R, XC. So what this capacitance reactance will do, it will make the current to lead the voltage, and it will not consume energy. So I think it's something very good element. No, capacitor, what it does, it will make current to lead voltage, and it will not consume any work for this one. You send the same signal, AC signal, across resistor. What it will do, it will make current to be in phase with the voltage, and it will dissipate power. It is bringing some changes by not consuming any power. Are you able to understand this? What is the capacitor? It is bringing some changes. What changes? It is making current to lead voltage. Is it doing any, it is spending any energy for that operation? No. It's just a storing element. Okay, let's see what happened to the power variation. Like earlier what we plotted, no? These are very small basics which we are going to carry out in the throughout this AC circuits. How the power cycle will be in this case. Average power should be zero, no? So therefore it should have positive and negative off cycle. So the signal, applied signal, oh, yeah, this is the applied signal. Will show for 1.5 cycle. Next again, what about the there's a current. This is current. This is the applied voltage. We have to plot the power cycle now. Okay, no. Yeah. What about the power cycle? So first, what we have equation? V naught I naught sine 2 omega t. So t equals to the power should be 0 only. So the graph will be this is one time period, no? T by 4, T by 2, 3T by 4, T. This should be 5T by 4 and this is 3T by 2. So what we get is like the power cycle will be it should be a sine off of the sine wave only. So I'm some rough diagram I'm showing it here. This is the instantaneous power I and this is E and this is a time T in seconds. So during one cycle, here it will consume power. Or you can say capacitor accepts, then returns back. So shall I put just positive? Positive means it will accept energy from the source. Negative power means it will generate or it will return back. Again it will absorb. Again it will accept. Again it will return back. Don't say positive, negative off cycle. Positive power means it will accept, the capacitor will accept. Negative power means it will return back. So in one cycle, what actually happens? In one cycle, what actually happens? There'll be exchange of energy between the capacitor and the AC source. So you altogether, how much power it has consumed, how much of power it has accept or it has drawn from the source, that much power it will return back. don't say consume, better say draws. How much of power the capacitor draws during this cycle here, during this interval, that much of power it will return back here. Again, it will draw the power from the source. Again, it will return back. So what is the net power dissipated? Zero, no? So therefore, what is the capacitor? It will not consume power. It will not dissipate power, better say. It's an energy storing element. There's exchange of energy between the source and the capacitor. And the twice that exchange occurs, first it will draw the power, energy, and it return back. Again it draws, again it returns back. In one cycle, the power, like when signal completes one cycle, what happened to power cycle? It completes 2 cycles. This is one power cycle. Because why that one? Why the, and this is signal cycle. Signal means applied voltage. By the time signal completes one cycle, the power cycle will complete 2 cycles. So sine 2 omega t is there. You see this one, 2 omega. This is only omega. Try to see this. So based on that, we are having this one. So what is the capacitor now? So what is the role of it? It will just make current to lead the voltage by 90 degrees. So therefore that reactance is what we have brought it. Of all, this is very important. And how to apply Ohm's law across capacitor? Not IR, I into XC. The drop across the capacitor should be off like this. And voltage and current are not in phase. You do remember. They are 90 degree out of phase. The current will lead the voltage by 90 degrees. So what capacitor will do? The capacitor will make current I'll write it here. The capacitor will make current to lead voltage by 90 degrees. There's a basic idea of the capacitor here. One more inductor is that I'll finish off this so that tomorrow we can directly begin with the concept. I'll continue for another 10 minutes. Oh, I'll continue. So for I think late, almost. Okay, tomorrow we'll see. No problem. That one. Tomorrow I'll continue from here. From response of AC signal to inductor, well, I'll continue from there because almost strength is only 70.
Sir?
Yeah.